So let's pick another function. Let's try and build another power series. Now, one of the things I like about the power series we've derived for e to the x is it's related to several other functions. So let's take a look at one of those. I again am going to try and build a Maclaurin series. So if I'm building a Maclaurin series, I'm going to build it with the center at 0. Which means I need to take a whole bunch of derivatives of sine. I need to plug in 0 over and over and over again and figure out a pattern. So I need the derivative, but I need to start with the 0th derivative. The 0th derivative is the function itself. So I'm just doing sine of x. What's sine of 0? Great. Derivative of sine, cosine of x. Cosine of 0 is 1. The derivative of cosine is minus sine of x, but minus sine of 0 is again 0. The derivative of minus sine of x is minus cosine of x. That's going to give me a minus 1. When I get to the 4th derivative, I get back around. So I'm going to have a repeating pattern here. Wait a minute. It's going to alternate between plus and minus 1, right? Plus 1, then minus 1. But there are all these zeros in the middle. I'm going to do one more set just so I have a larger group. To work with. So I need something that is positive at 1 and at 5, negative at 3 and 7. If I ignore the zeros, I would think I want an alternating thing, right? If I wanted an alternating thing that was positive first, then negative, how would I write it? Negative 1 to the n plus 1, right? Because then it would be positive the first time, and okay, wait a minute. So negative 1, n plus 1-ish. But this time, it's only the odd numbers. So it shouldn't do it every flip, right? It should do every other flip. An idea. Not 100% sure this is right yet, but I got an idea. What's the way to write an odd number? Because if you think about it, we're only 1 or negative 1 at 1, 3, 5, 7. 2 something plus 1 gives me an odd, right? So what if I write my n value as an odd number? Change variables. Because I have an n already, I don't want to use it again. This would force it to be odd. And now I can think of doing the plus minus flip in terms of the value of k, not the value of n. So let me go back up there where n equals 1. What's the value of k? K is 0. And here, what's the value of k? And here, k is 2. And here, k is 3. So if I think of my flipping back and forth in terms of k, I want to do minus 1 to the k to go with my n value being 2k plus 1.
How did you get k equals 0?
I said, okay, I'm going to put n in here. If n is 1, then the 1 cancels, right? N equals 2k plus 1. If I put 1 on this side, then k has to be 0. But now I have a pattern for that, don't I? Okay, wait a second. The nth derivative at 0 is minus 1 to the k when n is an odd number. And when n is even, we get 0. So it flips back and forth between 0, 1, 0, negative 1, 0, 1, 0. That works. That's a pattern for my nth derivative. And now I start thinking about Taylor's formula. Taylor's formula says that my function should be given by a power series since it's a Maclaurin series, we're using a equals 0, where Cn is Fn of 0 over n factorial. Yes? That's what Taylor's formula says without any filling in of the numbers, except for the 0. The only time I get something that isn't 0 is when I have an odd number. So for the even numbers, I'm always going to get 0. But for the odd numbers, I'm going to get minus 1 to the whatever over that number factorial. Means half of the terms in my power series go bye-bye. I can ignore them. I don't even need to count them. But I could think about this as being 0 when k is 0. Then here, I get negative 1 to the 0 over 1 factorial x to the first plus 0 over 2 factorial x squared plus negative 1 to the third, which is negative, over 3 factorial x cubed, 0 over 4 factorial x to the fourth, negative 1, that's going to be plus a 5 factorial x to the fifth, 0 over 6 factorial x to the sixth, and so on, right? So only the odd numbers end up mattering. Gesundheit. Try not to blow your ears out. That is a complicated as hell expression, isn't it? But if you think about it for a second, some amazing properties come out of this power series. I need to ask you an algebra and trig question. A long time ago in a galaxy far, far away. What kind of symmetry does the graph of sine of x have? That's a periodic function that is only part of the symmetry issue. There were two specific types of symmetry based on the way we looked at the graph compared to the origin. Odd, because what's up on the right is down on the left, and what's down on the right is up on the left. Why would we call that odd symmetry? Only odd powers. X cubed had that same symmetry. X had that same symmetry. X to the fifth has that same symmetry. It's because it's all odd powers. What about cosine? What kind of symmetry does cosine have? Everything on the left was the same as the stuff on the right. What do we call that? Page 768. Here are several commonly used Maclaurin series. The top one is our geometric series. The next one is e to the x, and we did that yesterday. The one I just did is sine x, and it's all odd. The one underneath it is cosine, and it's all even. Son of a random. Wait a minute. Inverse tangent. Inverse tangent is an odd function. And the power series is all odd powers. I do not expect you to memorize this list. I don't want you to memorize this list. Memorizing this list is a major pain in the ass. It's not worth it. But these top four are used so frequently in more general discussions involving series that they end up embedded in your head eventually. But it then allows me to get paid off by evaluating numbers. Like, let's say I wanted to know the value of ln of 2. I could use this series and plug in as many as I wanted. If I didn't have a calculator, I could do it as a fraction. For the record, this is the way logarithms were originally calculated. John Napier built a calculation device, a series of rods that would allow you to calculate a logarithm. It's kind of like an abacus, but instead of actually having beads, it had individual numbers written on it, and you turned it to line up the thing you wanted the logarithm of and your base. Interesting side joke. John Napier went to debtor's prison in the middle of all of this because back in the 1700s in England, they could throw you in jail if you owed people money. So they threw him in jail for owing people money. And the running gag was that he was kept working because what else you can do, sit around and stare at the wall. He kept writing math, and the rumor was that the first set of logarithmic calculators were made out of his cellmate. The nickname was Napier's Bones. It has nothing to do with that. They looked like a series of rods. They were made out of ivory. They looked like bone. This is crazy. This gets even crazier. Questions before I jump to the next piece of this? Remember, I said that this was the sine of x, right? This is sine of x. And then I just showed you in the book that cosine of x was all of the even bits. And with what we did yesterday, we had e to the x was the sum 1 over n factorial x to the n. All the bits, both even and odd, right? Well, that leads me to a really interesting idea. If sine and cosine are the odd and even pieces, same factorial idea on the bottom, same power of x as the factorial, and e to the x is the same idea, then these must be related. E and sine and cosine must be related to one another. And it turns out the only problem with the power series here is that I don't get the alternating part of it. This power series is always positive coefficients. These alternate. I need to introduce you to the best number in the universe. The imaginary unit, I, square root of negative 1. Remember this quadratic formula? We did that way back in algebra class. Well, wait a minute. If I is the square root of negative 1, then what's I squared? Negative 1. What's I to the 4th? The I squared squared, wouldn't it? Negative 1 times negative 1. Wait a minute, that means that I to the 6th is negative 1, because it's I to the 4th times I squared. 1 times negative 1. Hang on a second, just like sine and cosine go around in circles, I goes around in circles. I to the 8th is 1. I to the 10th is minus 1. Hang on a second. That cosine thing has even powers. The sine thing has odd powers, but it's I to the 2k. It's negative 1 to the 2k, right? If I take this number and put it in here, I can use the power series for that, right? Now that's going to be a major amount of algebra, and I'm not going to do it right at the moment. But every time I have an I to a second power, I'm going to get a plus or a minus 1, aren't I? And when I is to an odd power, I'll have one extra I left over. So all of the odd powers will have an extra I, and all of the even powers will have no more I's. They'll just be plus or minus 1. With a lot of rearranging. I end up with this. This formula is powerful enough to relate the 5 most important numbers in the universe. It turns exponentials in polar coordinates into numbers. I know 4 different people who like that formula so much they have it tattooed on their body. I am not one of them. The power series for e to the x changed the world. It opened up new avenues for exploring factoring of polynomials. Because really, what a power series is a polynomial on steroids. Questions? I did Maclaurin series. Well, we can do the same thing for any function at any point. That would be a Taylor series. So what if I want to use this, right? When we think about the convergence behavior, when we thought about linear approximations, we said, oh, it would be better to work near a point. So I could ask the same question about e to the x, or sine of x, or cosine of x. But then I could say, well, what happens if I pick a different center? I know. It would be useful to think about cosine. Near pi over 2. Now, one of the questions I get asked is, why is it useful to think about this? Well, a lot of work in optics deals with light coming in perpendicular to a surface. Exactly what you're doing, Maddie. I'm trying to get the light to come in at the right angle so I can focus on something. The purpose of spectacles is to bend the light, but the light's coming in perpendicular to the glass, isn't it? So I need to know what's going on when my angle's near 90 degrees. Or, that's just scribbled out.
No, function something.
Or any other function near x equals a. So let's try and do this power series. What is the value of cosine of pi over 2? Great. When I take the derivative, I get sine of x. Wait a minute, derivative sine is cosine, derivative cosine is minus sine. What's the value of negative sine of pi over 2? Derivative of sine is cosine, but cosine of pi over 2 is 0. Derivative of negative cosine is negative, negative, positive sine. Sine of pi over 2 is 1. Wait a minute, I'm in the same boat, aren't I? Only this time, it's flipping back and forth the other way, isn't it? Our previous example went 1, 0, 1, 0, negative 1. So it flipped the other way. Huh. So again, my goal is to try and find a pattern in these. And if I want to find that pattern, I need to start thinking about that even and odd routine again. About the 2k plus 1 and the 2k. But this time, all of our even ones are 0. And all of the odd ones, Okay, Dom, I need to do it again. I need to know which k value goes with which n. So here, k is 0. Here, k is 0. Here, k is 1 because we're in the even pile. Here, k is 1, but we're in the odd pile. See the way I'm getting the k's?
Yeah.
This would be the one where k is 3. Okay, so based on this, I'm going to have minus 1 to some power, but I want it to be negative when k is 0, positive when k is 1, negative when k is 2. What power should go up here in terms of k? Leo? I hope it's not 4 because negative 1 to the fourth is always positive 1. Well, that would always be negative 1 and it wouldn't change. I need this to be in terms of k. If I just made it a k, then when k is 0, it would be positive, wouldn't it? So that's not the right one. Let's use k plus 1. That way it flips back and forth as k changes, right? But the first time when k is 0, it's negative. Then it's positive. Then it's negative. Remember how we looked at sequences and tried to figure out a pattern for my sequence? I got to go all the way back to 11.1 to remember that crap. Or if you'd rather, you could say, wait a minute, that's minus 1 to the k, and then 1 extra minus 1, isn't it? To make it flip back and forth the right way. So now I have a power series. And this is the power series for cosine of x near pi over 2. Oops, wrote off the bottom of the screen. I will tell you that one of the harder parts of power series is finding these patterns. When we do Taylor and Maclaurin, that's going to be the bigger issue. But my goal in trying to find the Taylor or Maclaurin series is to write down the first however many powers I need and then figure it out from there. Yes, sir.
What does finding the value of k do for you?
Well, because this was in every other routine, I didn't want to put it just in terms of n because then I'd have to try and say, well, when n is odd, you do this. When n is even, you do this. By splitting it into the odd and even cases and using k instead of n, it made my series a little easier to deal with. Let's do one where I don't have to do that, because that seems to be the pain in the ass, right? Let me do one where I don't have to do that. We're going to do f of x is 1 over x. And we're going to do it centered at x equals 1. Now, this is where I will say with a perfectly straight face, 1 over x is not a polynomial. But what I'm about to write is a polynomial on steroids. I'm going to turn division into a polynomial. That's fucking amazing. Same deal. I want to make a chart. And you make the chart as long as you need to see the pattern. So I'm going to hope I can see the pattern in the first 7 or so. All right. F nth derivative of x. Well, I'm not taking the derivative, so I'm just dealing with x to the minus 1. Plug in 1. What do I get? I get 1. But now we start taking derivatives. What is the derivative of x to the negative 1? Say that again. And if I plug in 1, I get minus 1. Take the derivative of that. Leo?
It would be minus 2 over x cubed.
I don't want to write it over. I want to leave it in this power because I'm going to keep taking derivatives. But watch your signs. If I take the derivative a second time, it becomes positive 2. X to the negative 3. And if I plug in, I get 2. When I plug in 3, when I take the third derivative, the derivative of this is, and when I put in 1, I get minus 6. Wait a second. The next one. 1, 1, 2, 6, 24. I know those numbers. 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4. I bet the next one's 120. 5 times. And think about the way we got this. We took the 1 down here. We took the 2 down here. So this is really 1 times 2. This is 1 times 2 times 3. 1 times 2 times 3 times 4. Son of a negative 120. So I'm going to make the claim that I should have a factorial in my pattern. But also see flipping back and forth from pluses and minuses, don't I? Because these numbers keep changing signs. So I need some minus 1 to the something to get me that flipping back and forth. I don't know what that something should be yet. But now, I look at the factorials and I look at the n's. And the n matches the factorial all the way down. Now all I have to do is figure out what that exponent should be. I want it to be positive for the even numbers and negative for the odd numbers. What should this be? Again, it should just be an n. So now I can say that fn of 1 is negative 1 to the n factorial. Hey, let's check. What happens when n is 6? Should it be positive or negative? And it should be 6 factorial. The next derivative is 720 x to the negative 7th. When I put in 1, that'll be 720. What's 6 factorial? Grab your calculators. Leo, what's 6 factorial? It certainly will be. This matches my pattern. Now, power series. For 1 over x centered at x equals 1. It's going to look like this. f to the nth derivative of 1 over n factorial, x minus 1 to the n. Hey, wait a minute. I'm going to take this formula and put it in here. So what happens when I do over n factorial? And so my power series becomes minus 1 to the n, x minus 1 to the n. I just found a way to write 1 over x without ever using division. That's astonishing. But see how I had to find the pattern?
Yeah.
And that flipping back and forth with the plus and minus needs to be in there somewhere to check. By the way, I should work out the radius of convergence here. Because this does not have a radius of convergence of infinity. E, sine, cosine, inverse tangent, they all had a radius of convergence of infinity. This one doesn't. So let's find the radius of convergence. Out comes the ratio test. Now, fortunately for me, this particular an is fairly simple. So when I put this in for an plus 1, I get minus 1 to the n plus 1, x minus 1 to the n plus 1. And on the bottom, I have minus 1 to the n, x minus 1 to the n, but it's all inside an absolute value. What happens to my minus 1s? They're gone. And then what happens here? And that will be inside the absolute value. Now, what do I want to have happen? For this to converge, I need bingo. Which means the radius of convergence here is 1. Now, here's a sneaky thing. What function was this? What was the f of x I started with for this example? 1 over x. And we centered it at 1, right? If you were to draw the graph of 1 over x, what would happen at 0?
We're going up into infinity.
Because there's an asymptote there, right? This function is undefined at 0. I need to picture myself standing on the number line at the point 1. And I start to spread my arms until I run into a place where my function is undefined. Hit 0. Function's undefined. That's as far as I can go. My radius is 1. That works all the time. Ready? That function, we did that one already. We didn't do that Wednesday. We did that Monday. We did that with the geometric series twist, right? If you look back in your notes from Monday, I remember that this was the power series minus 1 to the n, x to the 2n. N goes from 0 to infinity because we wrote 1 over 1 minus negative x squared and did the geometric series trick. Question. Where is this function undefined? It's never undefined for real numbers, but it is undefined for complex numbers. Okay, I know you've seen complex numbers before. Has anybody ever showed you how to graph them? You take the complex number a plus bi and you graph it at the point AB. So what you're really graphing is on the xy plane, but you're graphing the a part, the real part, in the x direction, and you're graphing the imaginary part in the y direction. And that means that this is still the point 0. Where is the graph of the number I? Well, that's 0 plus I. So that would be graphed right here. And the point negative I is 0 minus I, so it would be graphed down there. How far away are those two numbers from 0? They're 1 unit away. Remember I said I was going to stand at the origin and I was going to push my arms out until I ran into something that got my function? I'm going to do it not as just on the x-axis. I'm going to do it in a circle in the complex numbers. And that's why we call it a radius of convergence, because right here, there's a little circle of radius 1. And my radius of convergence really does make a circle. Complex numbers are so cool here. Now, here's what I'm telling you. I am particularly interested in looking at power series because a couple of years ago, I taught a course called The History of Algebra. And I was looking in books to look up things like, there's a quadratic formula, there should be a formula for cubics, there should be other formulas. I found them. But in this particular book, I found a method for changing the center of a polynomial. And that's exactly what we just did here. We centered our function somewhere else. And I said, if this trick works for polynomials, it should work for series. And it works beautifully, perfectly for e to the x and sine x and cosine of x. You know where it doesn't work? Here. 1 over 1 plus x squared is broken for this formula. And I don't know why. I'm still trying to figure that out. So if anybody's interested in the research project, there's a poster about this on the first floor of Lynch, right outside Lynch 106, across from the water fountain there. That's my last presentation on this, and I have not had time to work on it since. But if you're interested, we can work on that moving forward. I think it's going to be a really cool result one way or another. If we can figure out why it works, or if we can figure out why it doesn't work. Both of those results will be important. That is definitely not on your exam. Good. But we can actually take power series and do a lot more with them. We can solve all sorts of interesting problems with them, including the problems in the next chapter on differential equations. But that is next week after the exam. So tomorrow is question and answer day for the homework. Turn that in Monday. We'll start our first look at differential equations, and then our exam is Wednesday. See you all then. Have a wonderful rest of your day.